So if I take t of the sequence, this here is nothing but the next element in the sequence. So this one here will still converge to x infinity, right? Because it's just shifted by 1. But then on the other hand, so now if you're looking at so you have that if you're looking at t, so we want to prove that right. So now if we're looking at t of x infinity, the distance between t of x infinity and t n plus 1 of x. Suppose I'm looking at this distance here, right? Well, this here I can think about as the distance between t of x infinity and t of tn of x. But here there are now both of these elements. You can think about this as just some element, apply t to it. Here there's t applied to that. So this is less than the distance x infinity to tn as a constant c less than 1 in front. So like this, right? By the contracting map property. But now you see that as n go to infinity, this thing here goes to 0, right? So this means that this thing here converges to this point, right? So you have that. So you have that. You have that if you're looking at right again as n go to infinity, since tn of x converts to x infinity, then we have that the distance, this is equivalent to that the distance here goes to 0. And then by this inequality, it means that the distance here, tx infinity and tn plus 1 of x goes to 0, right? And so this means that this is just some fixed point. It means that this sequence here, so this implies that this sequence here converts to t of x infinity, right? But on the other hand, we already observe that this sequence also converges to x infinity, right? But you so it converges to this and it converges to that, but it can only have one limit, so those two things are equal. So you conclude that x infinity is equal to t of x infinity. And so x infinity is a fixed point. Right, so this proved this theorem. Right? And again, we already knew that the limit was unique, right? Okay, so now how is this related to the Picard-Lindelöf theorem? And so it's related in the following way. And again, this is something that have been used to solve a lot of differential equations. And so we need to define space and a map. The space is initially, but we have to restrict it. But initially, let's think about some continuous functions on some interval. Let's start with just continuous function, but it's not quite going to be the space. I will have to look at a smaller, yeah? right. That's a good question. So that's right. So this comes with this Newton method. So we used this contracting mapping for R in the Newton method to find a zero. Okay, and to some extent, I mean, that was a great idea. Newton was a pretty famous guy for a good reason. But in a way, this is more ingenious, I think, because it's like, metric space. What the hell does that have to do with differential equation, right? And the reason why in the other one we had to restrict it was that the map we defined wasn't contracting everywhere. It needed things to be pretty close initially for there to exist a C strictly less than 1, right? So that's where it came in. It wasn't really because yeah. Okay. So now again, so we need to relate this. That seems to have nothing to do with differential equation. We need to relate it to the differential equation. So again, what is the space, the metric space that we're going to look at? And again, it's not exactly this, but it's just a subset of it. So it's this space, and with the usual metric that we have talked about, right? That is going to be the metric space. Now, what is the map T? And so the map T is, so T here is going to be a map from continuous functions into the space of continuous functions. And it's going to be defined as follow. And I'll come to this in a second. So T of x, T of y. So y, think about y as being a continuous function on this interval, right? And T of y is now equal to a plus, and then the integral, and then, right. Then the integral, so this is so T of y is an element here. This one here is also supposed to be an element here. So this is a function. So we want to find out what the value is at x. And it's a, this constant a, plus the integral from 0 to x, and then of f of y, plus g of x. And this here is a function of x, right? Also, like this. And I shouldn't write x because I use now x up here. So I write it like that, df. Okay? That's how the map is going to be defined. So again, if you take, so y here, so y is a continuous function on this interval. And I will have to restrict it. And this is exactly when you're asking what, in Newton's method, right? Why did we have to pick this good choice? It's exactly like this, that this map is not contracting on this whole space, okay? So we have to, in a way, we have to do the same stuff. We have to make a good choice first. And so that's why we have to restrict the space, okay? And it actually is, I mean, it's part of the beauty is that it's pretty much optimal, this stuff, this sort of general principle. We can come back to that. So this is the map T. And so the first thing that you observe is that T, so this gives you this function here, right? Remember that, so if y is continuous, g is continuous, if y is continuous, f is continuous, everything here is continuous. And so this means that by the fundamental theorem of calculus, this function here is actually even differentiable, right? And the derivative of this is just a constant. So this function here is differentiable, let alone continuous. So it's definitely in the space. And the derivative of this map by the fundamental theorem of calculus So by the fundamental of calculus, the derivative is just what is inside here. So this is just f of y plus g of x. Right? And if you want to write x in, then it should be like this. Right? So that's, so, and then one more thing you observe, which is also immediate, that if you take a continuous function like this, and now you evaluate this at 0, right? If x is 0, well then this integral, it's over just a point, so this here is 0, so this means that the value here is a. Right? Okay. And so now, the next thing you observe is that so the next thing we observe is that that if you have a fixed point, so if, I mean, I think this is another nice thing is that, you know, that the way it's set up is that you just need to use continuous functions, right? But of course, if you want a solution to this, it means that the function must have a derivative, yeah. Yeah, we don't know that yet. I mean, that's a major point, actually, right? And again, just like in the Newton method, we have to restrict where we're looking at it, yeah. Okay, so, but the first thing I want to observe is that if y is a fixed point, well then t of y is equal to y. And so what does this mean? Well, the derivative, so it means that if this is the case, right, then we have that t of y is of this form. So it has a derivative, and that derivative is this, right? So this means that y would have it, because y is equal to this. So y is differentiable, and the derivative is equal to this. And we always have, whether it's a fixed point or not, we always have that t y of 0 is a, and since it is a fixed point, this is also this. So you see that if it is a fixed point, then it is a solution to the differential equation. Okay? Now then, the point comes in, the key point comes in with proving that the map is contracting. Okay? Okay. And so we need to prove, need to show that T is a contracting map. Okay. So I define, so set, I have to define a number of things, because again, I have to, it's not, T is not going to be contracting on the space of continuous functions. So I have to look at some subset of continuous function. And the right subset is just a ball. It's a closed ball, so it's going to be, so we're going to, maybe I'll just say first, that we're going to restrict T. So T here will be restricted now to, we will think about it as a map on some ball into itself. But it's not at all clear that this map takes a ball into itself, okay? And what do I mean by balls? I have this bar up here. So I just means that this thing here is going to be the function y that is continuous. And then it's not quite going to be this either. I have to restrict, but I'll get to this in a second. So at the moment, you can think about it as being continuous function on the interval, so that the norm of y at each point x is less or equal to r. And this bar here refers to that that equal is also allowed. Right? Now this here is really like the board. Right? These are functions. If you're thinking about the function in the space of continuous function that is constant zero, right? Then these are the functions whose distance, this is the same as the space of continuous functions, whose distance to the constant function 0 is at most r. This is the 0 function, is less or equal to r. Sorry, this is getting a little smaller over here. Right, so it's just, okay. And again, it's going to be, I will have to restrict the interval here to make sure that the map is contracted. So, but first I want to define this radius here, okay? And so the radius is, so I'm setting r here equal, a was just a constant. I take the absolute value of a and I add 2 to it. Then I define two other, and there's no way around it. You have to define, we will require to define several constants first. L1, capital L1, is going to be another constant. It's going to be the maximum. And then you take of over z, where z here is less than r, and then you take the value like this. Okay? Remember, f is continuous. So if I'm looking at where the norm of x is less or equal to some constant, then the maximum is achieved on this. Right? So this is just some real number, positive real, non-negative real number. And then I define L2 to be the maximum of maximum on the unit ball here, on where norm of x is less than 1 of g of x, like that. Okay. And now, what I want to do is, the first step is the following. So first step in the proof is to prove the following, that there exist delta 0. This is not the delta that I will use eventually. I will have to restrict it further. There exists delta 0, so that if you're looking at the space, if y here is in the space of continuous functions on this interval here, then t of y, if y is in this here, and y is in the unit ball, and not in the unit ball, that y here is less or equal to r. Right, so it's a continuous function on this interval, and the norm is less or equal to r. So this means that, so this is of course the same as saying that y is in this ball here, when I'm now thinking about this as a space. But you can forget about that if you want. It's the same. Okay, and I want to show that T of y is in the same space, right? So I need, so T of y, so I want to show that T of y at each x here, the norm is less or equal to r. Right? Then if I have that, I already know that this function T of y is continuous. It's actually even differentiable, right? But it's in particular continuous. And if I have this, then I know that this space is taken into itself, right? Okay. So now how do I do that? So that's where I need to restrict the interval that I'm looking on. And again, we'll come back to it, but there's a good reason to restrict, that we have to restrict. Otherwise, it couldn't possibly be true. Yeah.
Where to be contracting, do we need it to be strictly less than?
So remember, contracting means that there exists a constant c strictly less than 1. This here had nothing to do with the constant c. This here is just the space that we're looking at the map on. Okay, so and the reason why I make here, so this have nothing to do with that c, but the reason why I want this less or equal to is that I want to have that the space is Cauchy complete. Okay, sorry. So let me just try to make that clear. So I have, to get a fixed point for a contracting map, you need a space that is Cauchy complete, right? That when we prove this for the metric space. We have a good candidate, right? We have the candidate of continuous functions on some closed interval like this, right? This is Cauchy complete, right, with the usual metric. But I'm not going to look at that space because my map is not actually contracting on the space. It's contracting on a subset, right? And so I need that subset. So in the end, I sort of, I'm not working on this, but I'm working on a subset, right? And I need that subset to be Cauchy complete. So basically what I have is that this here is the giant metric space I start with. Then I'm looking at a ball in this. And if I take the closed ball, and it happened to be at the origin, but it could be just at any point, right? If you take a metric space and you're taking something like this, if the metric space is Cauchy complete, then this subset is also Cauchy complete. But this require I have less or equal to, right? Because else it could kind of convert to something where you got equality, right? So that was why I do it like that. Okay, so let's see. So we have already defined this radius, capital R. And then we have these two constant, L1 and L2. And what I need to prove is the first step here is to prove that if I'm going to look again, so the first step is that I need to restrict. So I'm going to look at these spaces of, this is a subset of the continuous functions. And I need to prove that if y is in here, then the image is in the same space. Okay? And so this is the statement that if y is continuous, the norm of this function is less or equal to r. So at each point, each x, the absolute value of y of x is less or equal to r, then you have the same for the image under t. We already know again that the image under t of y is continuous. Okay. Okay. And so, what I can do is I can restrict my interval. So I will restrict the interval as follows. So I'm going to pick delta 0 to be the minimum of 1 over L plus 1. L is non-negative. In principle, it could be 0. I don't want to worry about that, so I just add 1. And L2 could also be 0, although it's pretty unlikely that any of them are 0, but I'm just, to be safe, I'm just adding so I don't divide by 0. So that's why, and the first thing is that and then I'm going to look at the interval from this, and this is not going to be my final. I will have to do some further restriction. But I'm going to look at this interval initially, okay? And the one here just comes in that I want this here to be a subset of this unit interval, okay? Okay. So now let's try. So now we are in good shape here. So now let's look at t, y, and we need to estimate this at each x, right? And we want to say that the norm is less or equal to capital R. But let's just look at what this is. This thing here is equal to this function t of y is defined to be a plus the integral from 0 to x of f of y of s plus g of s ds. And then I have to have absolute value like that. And now I can just use the triangle inequality, of course, sort of trivially. I get absolute value of this, and then plus, and then the integral here, like that. Oops. And then I can just take this absolute value in under, so I get less or equal to a plus, and then the integral, and then the absolute value of f of y of s. And here I can also take the absolute value using the triangle inequality on each individually. So I can write it like this. Now, this is where I use, so S here will have to lie between 0 and x, right? And so x is between, let me just draw it here. So here I have 0, here I have delta 0, and then I have, this is 0, and here I have x, somewhere x, right? But since, right, so this means that, so here you have x, but x itself, x has to lie between delta 0, minus delta 0, and delta 0. And s has to lie between 0 and x. So this means that s here lies between, x will lie in this interval also, right? But now you see that so now if we're looking at, so we have t of y in x, again, remember that x here is less than or equal to delta 0. So we have that this thing here is less or equal to a plus, and then the integral from 0 to x of f of y of s plus g of s ds. Right. And the first thing I observe is that s here is also, just because x was in that interval, you also have that s, because x is in that interval, s is also in this interval. The second thing I observe is that I'm assuming that the function that I start with at each point have norm less than r. Now, if I'm using these two things, then I have that, so this means that g of s, this one here, this is how we defined L2, right? Because this interval here is contained in the interval between -1 and 1. This here is contained in the interval between -1 and 1, right? So we have that g of s is less than this L2, less or equal to L2, right? The second thing we observe is that because we have this here, for each s, we have this, then it means, you see, by the definition of L1, that f of y of s, this thing here, is less than L1. Okay? L1 and L2 are now fixed numbers, right? And so you see that this second thing here, I can bound this thing here by, so this is less or equal to a, and that should have been an absolute value. Somehow I lost it when I copied from this line. A, absolute value of a. And then on the first one here, the length of this interval, but that is of course bounded by delta 0, right? So this is plus delta 0, and then the maximal possible value of this, that would be L1. And then likewise, the length of this interval you're integrating over is at most delta 0, and this one here cannot be larger than L2. So you have this, right? And now remember what delta 0 was, and I will just, I have it I think on the board below here, but let me just write it here. This here was what delta 0 was chosen to be. The minimum 1 over L1 plus 1, 1 over L2 plus 1. Okay? So now we have that this thing here is less than, this here we just keep. This thing here, well, delta is in particular less than this thing here. So you see that if you plug in this, so it's like plus 1 L1 plus 1 times L1. Likewise, over here, you're using this, so you're getting 1 over L2 plus 1 L2. And now you see that this thing here is less than 1. This is less than 1. So this is less than A. It's actually strictly less, but it doesn't really matter. A plus 2, like this. Okay. So this means that, so then, but this this here was exactly the definition of capital R, right? And so you have that, and when I copied it over, I also forgot to put absolute value sign here. Right? So you have that so the conclusion here is that if y here is a continuous function on this interval here, and the norm of y at each point is less or equal to r, well, then you have that t of y at each point is less than r, less or equal. It's actually strictly less, but we don't care about that. Okay, so what you have now is, so what we now have proven is that we have this map T, and now I'm going to think about this map, on the space of y that is continuous on this interval here. And what you have is, and I'm thinking about with the norm at each point, this here is less than r. And again, this is really a ball in this metric space, but let me just write it out like this. And what you have is that, this is the space, and you have that t of y. If y is in this space, then t of y is in the same space. So t of y is also continuous on that interval, and t of y at each point x is less or equal to r. So the map this space into itself, okay? Now, the next thing we want to prove is that the map is contracting, okay? But you see that you need, if the space is not stable, right? So imagine that you take, we're starting with some giant metric space. This is the continuous function, say, on this interval. And then we're looking at some subspace of that. So these are continuous on a smaller interval. Okay, and then we have defined a map. But if if somehow the map was taking us out of the space where it's contracting, then we couldn't keep applying the contracting map, right? It wouldn't anymore be, and the thing is that you want to just iterate. You want to pick some point, and then you want to keep applying the contracting map. So you want it to stay in the space where it is contracting, right? And so this is what we did in one. But we haven't yet proved that the map is contracting. And so now to prove that the map is contracting, we're going to further restrict the interval, okay? And so I'm going to define now one more constant, about that. So this is m here. And m is going to be just the max of f prime of z, absolute value of this, where z here is less or equal to r. Fine. So this is my almost the second last constant, unfortunately. And now I'm going to define this. So the last constant is going to be the interval that I'm going to work with, right? So remember what I'm trying to do is I have this differential equation, and I want to say that near zero, there is a solution. But near zero just means that there exists some tiny interval around zero where I have a solution. And again, if I have time, or else I will do it next time, I will give an example where you can see that in general, you would need to look at a very tiny interval for this to have a solution. Otherwise, it doesn't have a solution on a very large set. Okay, so I define it like this, and then I define delta here. So delta is now going to be the minimum of delta 0, the one from before, and then 1 over 2m plus 1. And now I want to look at the space. So I want to look at T, and then T is going to be a map from the continuous functions. So y here is a continuous function on now this little interval. So this interval here, because you have the minimum of this interval is contained in the corresponding interval with the delta 0. So it's y in this space such that the norm here at each point is less or equal to r. That's the space I'm going to look at, and we already know that T maps this space into itself, right? Because there's really no new statement. If the function is right, so as long as you have this here, and you apply T on it, when you apply T on a function, it's defined on the same interval. So it will automatically define on this smaller interval. And we already have this property. Okay, so T maps this space here into itself. Okay? And now I want to prove, I want to estimate, so I take two elements in this space. So I have y1 and y2. So you're looking at, so y1 and y2 are in this space. And you want to look at what is the distance between y1 and y2. Right, so we want this here, and we want, what I want to prove is that it's contracting. So I want to show and I want to prove, I'm going to prove it. You know, my constant C will be explicit. It will be just a half. So that certainly is less than 1. And this is what I want. Okay. So now, let's look at that. So T of y1 minus T of y2. This thing here, T of y1 is defined to be a plus the integral. Sorry, and let me write, so I'm going to, let me just make a little more space here. I worry I'm running out of time, but let's see. So this thing here, minus T of y2, and I'm just looking at the difference in some x. And again, x here is now in, x here will be in the interval. You were looking at x in the interval, in this interval. And so I'm just writing down first here what this is. This is the integral from a to x of f of y1 s plus g of s. And then you have minus, this is what you get for a2, for y2, a, so minus this thing here. So this is the difference, right? And what you see is the first thing you observe is that this a's here cancels, right? But it not only does this cancel, but this term here also cancels, Okay, and that actually, there was a good reason that they were lower order, and the point here is that, right, the main point is in the unknown function anyway, right? And it's a what's called a nonlinear equation. So that's a difficulty. So, but what you then get when you write down, when you have after the cancellation, what you get is f of y1 of s minus f of y2 of s ds. Okay, so you have that. Now I will look at this thing here and that thing here, and I'm going to, and you have to now abstract. So now I'm going to look at this difference here. And then now the thing is that you have to kind of abstract from it, and you have to think about S as being, if you think about S as being fixed, right, then this is just two numbers, right? You could think about this as Z1 and this here as Z2, right? This here is Z1 and this here is Z2. So it's like f of Z1 minus f of Z2, right? Now, the mean value theorem tells us that this thing here is equal to the derivative at some intermediate point, let's say Z3, where Z3 is between Z1 and Z2, right? And then times Z1 minus Z2, right? And but you, okay, so this is just for for any xs you have this, okay? But this means that now we're almost out of time. So this means that when you're looking at the norm of this, f of y1 of s minus f of y2 of s, right? That the norm here is, so the norm is equal to f prime at Z3 times Z1, which is, and Z1 I can write in, it's really this, and this is Z2. This thing here, remember Z is some point in between those 2 points, right? But both of these points here, both this one here and that one here, have norm less than r, right? So this here is, so, but now where the way that M was defined, and it should have been on the same board. So M here was defined to be the maximum of f prime of Z, where Z was less or equal to r. And so you see that this thing here, where you take the derivative, that is bounded by M, right? So this thing here is less than M y1 s minus y2 of s, like that. Okay, so I'm not sure where we should stop. I mean, we're over, and I probably need a few more minutes. Maybe we should stop. And it's not a great place to stop, but that's how it goes. So I will keep you in suspension, and so we'll pick up from here on Tuesday. And so I want anyway to explain to you why actually this method, which seems a little crazy in a way because it's bringing in all these things, why it turned out to be basically optimal. Okay. And then we'll do a review the rest of the time on Tuesday.